polynomials. Today we're going to talk about what is a polynomial, we're going to talk about what's the degree of a polynomial, the leading coefficient, and what is standard form for a polynomial. Most of this will be review, hopefully, but there will be a new piece because linears you know all about. You've been doing those since Algebra 1. Standard form for a linear is ax plus by equals c, right? You just have an x and y. So what is the highest degree of your x in a linear? What degree is that? 1. It's a first degree, literally. It's a first degree because your highest exponent of your x is a 1. And so, yeah, it's a first degree. Quadratics we know to be x squareds, right? We've been spending, gosh, lots of time on them this semester. And that standard form would be ax squared plus bx plus c equals 0. Some books, even up here, will call this minus c equals 0. Some books put the c on the other side. The point is that the exponents on your x go from highest to lowest. That's what makes it a polynomial. So we're just going downhill on our exponents using a, b's, and c's as coefficients. What degree is a quadratic? 2, which would be a second degree, right? And literally, when you graph a linear, it literally just has one dimension to it. It goes up and down. That's all it does. Whereas when you get into quadratics, then all of a sudden we have an x and a y, and they make parabolas, right? So this can be set up as y. Then your cubics, what is our degree of a cubic? If we have a bunch of cubics, you see them. This would be an ax cubed plus bx squared plus cx plus d equals 0. What's that? Yeah. Sometimes you can. Sometimes you can, not always, but sometimes you can, yes. Because we've done that. We've had 4 terms. We've had cubics, and we've done that. So where do you think the word cubic comes from? What's the degree of the cubic? 3. How do you connect a 3 with a cube? Yeah, it's 3-dimensional, right? Think about a cube, a box. A box not only has length and width, but it has depth. So literally, the cube means, it's a 3rd degree, and now you're not only going up and down and left and right, but now, you've got the whole cube effect, where you've got a depth to it. So that's why they call it cubic. And it will be starting in the x cubed. Anybody want to make gander what x to the 4th is? I mean, it even talks about this. Quartic. That's right. It's a quartic. Q-U-A-R-T, quartic. Quartic. You can think of 4 quarts to a gallon, 4 quarters in a dollar. That would be ax to the 4th. And then start going downhill to the 3rd. To the nothing. And I don't know how to draw 4th degree. But it's obvious to see why they have 4, why they call it quart. Because 4. Like that. And to the 5th power, do you remember that one? Quintic, good. Quintics to the 5th power. So, what do we do with these polynomials? Well, one of the things we do is evaluate them. And you've been evaluating these for a very long time. Again, when you have a problem like this, usually what the directions were in your pre-algebra was, what's the value of this expression when you substitute x in for the 2? It was a kind of, in your head, it was taught as a substitution problem, right? And it's no big deal. The only problem is that now with our substitutions, they're going to be bigger problems because we're substituting in polynomials. Some of them will have 5 or 6 terms. whereas in younger grades, you usually only have to plug it in one or two places, but we're gonna have to plug it in a lot of places. So we wanna make sure that we know how to plug in with a bunch of exponents on your particular calculator. So I'm gonna give you a minute, I'd like you to get out your calculator. And the biggest difference, or the biggest thing I would say is gonna be with your calculators, is learning how to use a parenthesis whenever you're plugging something in. That's not that big a deal in your lower grades, because usually you just plug in positive numbers or things that you know what that first power is or whatever. It's gonna be different now that you're getting into more complex problems. So literally, let's get in the habit of going 3 parentheses, whoops, my x is a 2, close parentheses, raise that to the second power, plus 2 minus 3. Tell me what you're coming up with.
11.
What is it?
11.
11. Okay, anybody have a problem with that? Plugging it in, if I know where your buttons are. You just raise your hand up at any point we have a problem that you don't know what to do with. Okay? Yeah. It's like with this guy. Huh? Okay. 317. Good. Okay, this time, this is the exact same problem, just with more sophisticated verbiage. But it's the same thing. In your book, because you're in Algebra 2, it's going to say, use synthetic substitution to evaluate the polynomial function with a given value of x. It means the same thing. Okay? So, and that's the same problem even. So we would do that no differently. Stick a -3 in wherever you see an x. Yeah. Same problem. All right, here's what I'd like you to do. Get on a piece of paper, on your piece of paper, set up 4 columns. One for the type, another column for equation, another column for sketch, another column for end behavior. Because the first thing we're going to sketch is just a linear that you know how to do this. Do not put this in your calculator. Just y equals 3x plus 2. The type is a linear, we know that. What is the slope of that line? 3. Right, 3/1. So the slope is 3, so that's a positive, so it's going to lean which way? Right. So if I were to draw a sketch of it, it would look like that. Right? So what's this end behavior thing? Well, every problem has 2 ends. It has a left end and it has a right end. And so you want to describe what's happening at the 2 ends. So the way you'll write that is, in this case, this one's starting down and it's ending up. So it's just going to be a down to the left, up on the right. Right? Again, we don't need a calculator for the next one. What happens if we put a -3 in there?
Stolen.
Yeah, it's going to be, but it's going to be still going to be linear, absolutely.
It's going to go from up to down.
And go from up to down, I like it. Lean to the left, fall from left to right, however your algebra ones you're talking about. So this is going to change my end behaviors, isn't it?
So up.
Now it's going to be up, down. The next set we are also not going to use the calculator on because you are pros at quadratics. This is a quadratic. I know it's going to be a parabola. I know that the A, the leading coefficient, is a 1, which is positive. So it's just going to be this. So meters. And then, of course, if we stick a negative in front of it, change our A to negative, it's going to flip it around the x-axis. Reflect it, I should say, more efficiently. Reflect it over the x-axis. And over down. So you have it down. Nothing new there, nothing surprising there, because you know how to work graphs. Those by hand. In your school. But let's move to some that you don't know what they look like. What about a cubic?
do this.
So, we're gonna graph that in your calculator, and let me tell you the buttons you're gonna push. So when you stick the cubic in, you'll see that the positive A, you'll see the shape there when you graph it. Make sure that when you put in the negative, this is the negative sign that's down toward the bottom of your calculator, the bottom of your numbers, that is the negative sign. And it will kind of have the same shapes that go in. Again, if we were standing on both ends of the arrows and pulling them, it would have a negative link to it. So that makes sense, that would be have a negative in front. That bad boy is starting up in the tip. Okay, so that was new, hadn't had that one yet. Let's try the quartic. Let's test that little guy. So grab x to the fourth plus 1. So it looks a lot like a parabola. There is a little, if you were to zoom in, which don't zoom in, I'm just telling you. They can, depending on how much stuff you have after the x to the fourth, this can get pretty kinky down here. But looking at it from a long distance away, you would think it's a parabola. You wouldn't see that detail of kink at the bottom. So yeah, we've got up. And knowing what you know about parabolas, what do you think's going to happen when we stick a negative in front of that? All right. It's just going to flip right over the x-axis. Exactly right, yeah. It either ends up being kind of a W or an M. For McDonald's. Oh yeah, yeah, we did do that too. So what about the quintic? You think that's something we do here? For some reason I don't have it in my chart, so let's do quintic. Let's just keep it easy. Let's do x to the fifth plus 3. That in? Yeah, it's a squiggly again. Looks like the cubic. It should look just like the cubic. It does this. I'm exaggerating it, but yeah. But it still has, starts low, has one kink in it, ends high, right? Now we're going to start looking for patterns, but to help you do that, this has no name, but if we graph y equals x to the 7th, do that to it. What does it look like? Cubic with the, still got the basic shape of the cubic and a quintic? It's probably getting more spread out, isn't it? Or skinnier? Yeah. Yeah. I'm drawing these two spread out. They should be more like that, really. I'm exaggerating a little too much. So, just out of curiosity, what would y equals x to the 51st look like? That's a good question, but we're not going there. Okay? So, look at your chart. Look at the exponents, look at the end behaviors, and see if you can't come up with some patterns that we could write a few rules to know how to graph things. So at even degree, they'll both be up, up, or down, down. If it's a negative leading coefficient, if your A is negative, they'll both be down, down. Positive will be up, up. So how would we describe the odd ones then? Look at those end behaviors. Every odd end behavior, how would we describe that? Yeah, they're opposite to one another. I'm going to call it mixed. They're mixed. One's up, one's down. Now here's the trick question though. How do you know what is the original, whether it's a negative or positive A? Can you see a pattern between correlation between it and the end behaviors? To give you an idea. Look at the, instead of starting though, look at the ending. Look at all the ones with the negative in front. How do they all end at the right? The very far right. What's the indicator on the far right? Down. So if your A is a negative, then it's going to end down. If your A is positive, it's going to end up. Okay? So by knowing the leading coefficients and the exponent, we can get the general shape of anything we want without even using the calculator. So if it's a positive leading coefficient, gosh, this is little. Okay, so if it's even, positive leading coefficient evens, they're going to be up, up. Or odd, so if it's an even, a positive leading coefficient, it's going to end up, so therefore it's going to start down. Negative leading coefficient, if it's an even, and then go down, down. If it's an odd degree, it's going to end down, therefore it's got to start up. This is a more sophisticated way to describe ending behavior. Let's say we have a graph, let's just use an odd power like this, okay? When I'm describing what's happening as I'm going to the left, the x's, this stands for approaching, and you'll see this arrow meaning approaching a lot going in your higher math classes. So what's happening is x is approaching negative infinity, because I'm going further and further to the left. This guy's going to go further and further to the left. And I would read that as x approaches negative infinity. To describe the right behavior, in my drawing, x is getting bigger and bigger and bigger, and as it gets bigger, of course, this is going to go up, but my x is going toward positive infinity, the right. Then if I'm describing up and down, it's going to be the same. When you go up, the y is approaching, and we just will do the same. Though in this case, the y's are approaching infinity, because this is going to get higher and higher and higher. And going down, we would describe that as the y's going further and further down, and that would be for a negative infinity.
If you're going left for the
So let's move on. All right, so let's see what we can do with these now that we know the patterns. We're going to sketch, well, not we're not going to sketch yet. What is the degree of this problem? What do we need to do first?
rearrange it.
Yeah, we have to put it in standard form first. Yeah, be careful. So this is negative 4x to the 11th. Don't forget to do that first, otherwise you'll get fooled like you just did. So the degree is, leading coefficient is, therefore, the end behaviors are going to be what? Good. I know it's going to end down because my leading coefficient is a negative. I know it's going to be mixed, though, because that is odd. Then, of course, we'll start up and down. And that's a 7th degree, man. You're doing great.
11.
Like I said, it's 11th degree. It got me.
It's okay.
All right. We also have certain behaviors at the zeros, at the factors, at the roots. All of those numbers mean the same. Have we used the word multiplicity yet in here?
Yeah.
When something is squared, so like right here, if we had this equation, this is in factored form, right? And we were going to graph that, remember how we said, okay, we would have a root at a positive 7. 1, 2, 3, 4, 5, 6, 7. And we have one at negative 2. But because of this 2, what's going to happen to the graph here? Remember, have we talked about that yet? No, it's not going to make a parabola. Because we need to know, if I end up FOILing this all out, what's going to be my highest degree?
Oh.
It's going to be x cubed. Because this is going to end up being an x squared along the way. That's going to have to be multiplied by this x. So this is a total of x cubed. So this is an odd degree. Even though it doesn't look it right at the beginning, you got to think it through. So it's an odd degree. The a, there is no a, therefore it's a positive 1. So I know it's going to end up. So that means it's got to start down. But if I start up here, go through the negative 2, if I go through 7, how am I going to get back up without hitting it again? Well, sort of, yeah. You bounce. I have to bounce at 7. We call it a bounce. And as a matter of fact, anytime you have an even degree, an even exponent outside a factor, it's going to bounce. So let's put on this note here. So if you have a multiplicity that's an even multiplicity, then you're at your x-intercept, you're going to have a bounce. In your graph. So right here we had at x minus 7, this was squared, so we had to bounce at 7. Because we had to end up, because we had to start down. It's still a 0, because it's still our x-intercepts. If you were to set this equal to 0 to find your x-intercepts,
So this is like x0,
x0. Yes, those numbers are, yes. Yep, that's exactly right. Yep. Now, how would you think you describe the multiplicity of an x-intercept that was odd? What do you think about what experience of that we've had so far? The experience we've had so far, think about the cubic. What happened to it when it got to the x-axis? It went, yeah, it did a little rare. I call this a squiggle. The book doesn't call it anything. I know Miss Turpin calls it a twist. I don't know what to call it, but it does a little jig. Okay, it's not going to bounce. It's not going to go through nice and straight. It's going to do a little jig. So you can call it a jig. You can call it a squiggly. But it's going to do something kind of kinky right there. Okay, it's going to be kinky. It's not going to be nice and smooth. So what the heck? So let's put all that together. Now that we know what bounces and squigglies look like.
Can you explain again how that equals to something?
Yeah. Okay. If I were to, I would have to FOIL this piece, which would give me x squared plus 2x plus 1. And then I'd have to multiply by this piece. So I would have to distribute this x to all of those things and then distribute by 3.
Okay.
And this x times this x squared is going to eventually be an x.
That makes sense.
All right, so let's do exactly what Stephen was just doing. What is going to be my eventual degree? Okay, I've got a third degree. My x-intercepts, where are they going to be?
on the 3 meters.
Yep, at -1 here and at 3 here. So -1 and at 1, 2, 3. However, this one is a square. So what's going to happen at -1? It's not going to squiggle. It's going to bounce because this is an even exponent. So I'm going to put a B here to remind me to bounce right there. Okay? And then the other one is just the first power. It's just going to go straight through. All right, so let's make that happen. Leading, oh, the A is a negative, so I know it's got to end down. Let's see, the x-intercepts were, I think this is what you were talking about, Jessica, the x-intercepts were -1, 0, and yeah. Oh, we need to find one other point before we put this all together. The y-intercept. But wait a minute, is that a big deal? What happens at the y-intercept? What is always 0? X. We're just going to stick a 0 in for x. It's no big deal. So 0 plus 1 is 1. 1 squared is 1. -1 times -3. Times -3. Careful, we're multiplying. Okay. So the y-intercept is 0, 1, 2, 3. So I need to make all of those fit together, starting up, ending down, and bouncing at -1. Okay? So we're just going to go bounce up, down 3. See, I think we should. So the end behavior, we're going to be up. B for bounce. I should put B there, remind me to bounce there.
So when you're writing,
Good? Okay. All right. Ooh, look at this one. Negative x parentheses x minus 1 parentheses cubed x plus 5 squared.
Whoa.
Let's do some analysis first. Okay, first let's find our x-intercepts. Well, no, first back up even more than that. How many factors do I have here? 3. Careful. Wait. 1 here. Well, actually, I got a -1 in the front. That's 1. Then I got an x. 2. Then I've got 3 of those. Makes 5. And 2 of those makes 7. I have 7 total factors there. What just happened? I could write this as -1 times x minus 1 times x minus 1 times x minus 1 times x plus 5 times x minus 5.
Oh,
That's 7 factors. Okay? So if I was solving this problem, I would need 7 answers. And we'll be doing that.
oh, no.
Okay? It's no big deal. All right. So where are my x-intercepts? Well, this could be, if that x was 0, the whole thing would be 0. Okay, if this were a 1, oh, I did that backwards. So at 0, and at 1, and at -5. 1, 2, 3, 4, 5. Okay. So, what's going to happen at the -5 right here? Because it has an even exponent. It's going to bounce. I'm going to put a B here to remind me to bounce. What's it going to do at this 1? Yeah, do that thing. It's going to do that thing. It's going to twist, squiggle, kink, whatever you want to call it. I'm going to put a T for twist. And I'll put a K for kink. Where is that? At 1. I'm going to kink or twist or something here. What is the total exponent going to be? I have 1 here, plus 3 here, plus 2 there. So I'm going to have a total of 6 x's. Therefore, that's even. Therefore, they're going to both be up or both be down. Ooh, this is a negative. So they're both going to be down. So I'm going to start down and end down. Let's find, oh, you know what? Our y-intercept, I've already found it. My y-intercept is at 0, 0. All right, so we got to make that happen. Let's think about it. So I start down, I'm going to bounce. Oh, I totally missed. I'm going to bounce. That was so bad. Ugh. No. Okay, so we're going to bounce. And then we're going to go through here, right? And then we're going to kink here. Okay, let's talk through that. So I bounced here. because that was to the second power. I went straight through at 0, because that was to no power. And then I did a little dance, a little kink at 1, because I had an odd power on it.
How much of a team do you think?
Just enough to be seen.
What about the time?
Well, bounce is a bounce.
I don't know what that is. You can be writing on all the time.
Oh, because I totally missed the dot. I mean, you need to hit this, point. I didn't hit it. Yes.
How do you find
How did I get the what?
the negative x?
The negative x.
One starts down,
Yes.
that point.
How did I know it? This point right here?
Point.
Oh, because right here, when I took the square root of 18, I set this equal to 0, the x squared minus 8. Worked that out, and x ended up being plus or minus the square root of 18. So you need both positive and negative.
I didn't know whether that's after it hits the one.
Well, if you have an even exponent outside somewhere, if I had a 4 here, a 2 here, I'd be bouncing. But I don't have anything outside.
So 2 is about 3.
2 is about evens or bounces, odds or squiggles. This.
Yeah.
Okay? Gross.
It's a lot.
It is. What if they give you to it in, it to you? Standard form. Don't freak out.
Where did you put that?
You can, well, if we do think about factoring, what's chemical and all that stuff.
You can pull it in there.
Yeah. And if you have a negative exponent, it's going to pull out a negative x to make our quadratic kind of nice inside.
Plus.
That good? And so, let's just factor this little guy, it's a mini mark, no biggie. Plus 9 minus 2. No big deal. So we've got 3 zeros. We got one here, one here, one here. Y'all know so much about quadratics now that nothing should worry you. You've got lots of tools in your toolbox. It hasn't been your time yet. Positive 2. In the factored form, was anything squared or cubed or anything?
Yes. No.
Now, there's no exponents outside the factor, so everything's going to go straight through. It's going to be an odd exponent. I don't have to add any exponents together, and it's a negative. So that means it's going to end down. That means it's going to start up. What do you look at before you know it's down? I am done. You will need 7 graphs, the ones in red are to be graphed. I'm going to hand you a piece of graph paper. Here we go, 7 on.